Hello and welcome back. So in a circuit which contains inductance as well as a resistance, such as the one shown here, when the switch is closed, the current does not rise immediately to its steady state value but rises in exponential fashion. This is due to the fact that the back EMF is created by the changing current flow through the inductor. This back EMF has an amplitude which is proportional to the rate of change of current, which means that the faster the rate of change, the greater the back EMF, and a polarity which opposes the changing current in the inductor that caused it initially. The back EMF is produced because the changing current in the inductor causes a changing magnetic field around it, and the changing magnetic field causes, in turn, an EMF to be induced back into the inductor. This process is called self-induction. Now, because the back EMF opposes the rapid change in current taking place in the inductor, the rate of change of current is reduced, and what would be a vertical line on the graph becomes a slope. The rate of change of current through the inductor is now less, so a smaller back EMF is produced. This allows the current to increase further. The relationship between the changing current and back EMF produces a curve which always follows a mathematical law to produce a particular shape of curve that is an exponential curve. When the switch is open, the current decays in a similar exponential manner towards zero. Now, looking at this figure, which shows the voltage across the inductor, we can see that at switch on, the voltage immediately rises to a maximum value. This is because when voltage is applied to the circuit, little or no current is flowing because the inductor is seen for a very short time as a very high resistance due to the back EMF effect caused by the rapidly changing magnetic field around the inductor, inducing a voltage, which is called a back EMF, back into the inductor, which is in the opposite polarity to the applied voltage from the supply, and so initially opposes the increasing current through the inductor. Because of this opposition caused by the back EMF, it appears initially that the inductor has a very high resistance, and so the full supply voltage is developed across the inductor. As current through the inductor begins to build, however, the rate of change of the magnetic field reduces, the opposition due to the back EMF reduces, and the apparent resistance of the inductor falls to a low value. And as a result, the voltage across the inductor decreases until a point is reached where the wall of the battery voltage is being developed across the resistor R. The voltage or potential difference across the inductor is practically zero, and energy is now stored in the magnetic field around the inductor. However, when the current is switched off, the magnetic field is now collapses instead of growing as it did at switch on. This collapsing magnetic field now returns its energy into the inductor coil and induces a voltage, which is called as back EMF, into the inductor. But because the change in magnetic field strength is in the opposite direction to the expanding field at switch on, the induced voltage is now in the opposite polarity as shown here. The rapid collapse of the magnetic field as the switch opens can cause very large voltage spikes, because the amount of voltage induced is dependent on the rate of change of the magnetic field. The high voltages produced can lead to arcing at the switch contacts, as the voltage jumps the gap between the contacts. These large voltage spikes can also damage other components in a circuit, especially semiconductors, so care must be taken in the design of circuits containing inductors or driving inductive loads to prevent these spikes. So let me show you a practical example of when this back EMF introduces problems, and I will show you as well how to prevent it. First, let's take a look at a DC motor. Every DC motor has 5 basic parts: a shaft, brushes, stator magnets, rotor coil, and a commutator. In most common DC motors, an external magnetic field is produced by high-strength permanent magnets. The rotor, together with the shaft and the attached commutator, rotates with respect to the stator. The rotor consists of windings, generally on a core, and the windings are electrically connected to the commutator. So why am I showing this to you? Because I want you to realize that when you are dealing with motors, we are in fact dealing with inductors. The symbol of a DC motor is this one, but for this occasion only, let's replace this with the symbol of an inductor, and don't worry, we won't go wrong by doing this at all. So let's create a circuit so that we can drive this DC motor somehow. We need a device or a circuit that can turn on and off this motor using a small electrical signal. For this, we will use an electrical component called a transistor. Using a transistor, we can drive the motor with a high current using a small electrical signal that might come from an integrated circuit, for example. Of course, in the simulator, we will use a switch on the base of the transistor to simulate this behavior. And here we are. So I know we haven't learned about transistors yet. However, this is a very good example to show you that back EMF can cause really big problems. So how does a transistor work, you might ask? I won't go into detail because that would go beyond the scope of this lecture, but what we have to know for the moment is that since we have an NPN transistor here, the transistor will allow current to flow from 20 volts to ground if there's around 0.7 volts between the base and emitter of the transistor. So transistor has three legs. This is the base, this is the emitter, and finally the collector. Current will flow from collector to emitter when the base is with 0.7 volts higher than the emitter. The emitter leg, as you can see, is connected to ground, so 3.3 volts on the base is more than enough. However, I have chosen 3.3 volts because most microcontrollers, like Arduino for example, can output either 3.3 volts or 5 volts. This resistor here is used to limit the current flow so that we won't create a short circuit between these 3.3 volts and ground. Don't worry if you don't understand transistors yet, you can always come back once you learn about them. So the goal of this circuit is to turn on and off this motor here. How do we turn it on? By turning on the transistor first. So when I close the switch, current will flow through the motor and it starts spinning. What we are interested in here is the voltage that is present on the collector of the transistor. Unfortunately, there is a problem with the simulator here and the voltage on the collector keeps oscillating between two values. However, normally there would be a constant voltage of 20 volts across collector and emitter. So if I take this motor out for a second and connect this directly, you can see that 20 volts is dropped across the collector and emitter of the transistor. The voltage coming from the power source must be dropped somewhere until it reaches ground, which is always at 0 volts, right? So the whole voltage will be dropped across the transistor. We know that over time the voltage drop across the inductor decreases to 0, so practically there should be 20 volts here. And I forgot to mention that if you want to check the voltage with respect to ground on a piece of wire, just double click on it and click show voltage. So everything is good, the motor is spinning, and there's 20 volts on the collector of the transistor. Now let's suppose you want to turn it off. You open the switch and notice the back EMF in action. The voltage on the collector suddenly rose to negative 102 kilovolts. There's no transistor that could handle this voltage on its collector, so once you turn the motor off, you can as well throw out the transistor because you have blown it up. In real life, the voltage here again wouldn't oscillate like here. There would be a huge negative spike that would instantly blow up the transistor. So what can we do to protect our transistor so that we can safely turn off the motor? Well, back EMF cannot be prevented, but it can be controlled. In suppressing the back EMF, the objective is to prevent the very high voltages and dissipate the stored energy in a controlled way. There are a number of ways to do this, and we will look at one of the most common methods used. So the most common method is to use a flyback diode in parallel with the inductor. So there are more types of diodes that we will learn about in the future. For now, just remember that flyback diodes are used for protection against this back EMF voltage spike. You can look at it as a regular diode. Now, the basic idea behind the use of a flyback diode is to provide an alternative path for the inductor for its current to flow. What's important to remember is that the diode is connected in reverse biased when the switch is closed, and as a result, the diode doesn't impact the operation of the rest of the circuit when the motor is spinning. But when the switch is opened, the change in polarity of the inductor will make the diode to place in forward bias. So when the switch is open, the inductor will reverse its polarity and the diode will be forward biased. While forward biased, the diode will allow current to flow through and dissipate at the rate the inductor wants. So as you can see, the addition of a diode gives a path for the current to flow. Since diodes have almost no resistance when forward biased, the inductor only has to make a very small voltage drop to get the correct amount of current to flow. This prevents the switching device from arcing or being damaged. It is important to note that the diode's polarity must be opposite of the power supply, and this ensures that when the switch is closed, the diode will have no effect on the circuit, essentially looking like an open circuit. This also means that when the switch is open, the diode's polarity will match the inductor's reversed polarity and prevent a serious voltage spike.